We are from Group 1. We'll present about the microporous ceramic membrane for separation application. Okay. These are our group members. So the first is Ain Afifah binti Abdullah Afendi. Then Prasan Kumar, anak lelaki Ramas Kumar. The third one, Muhammad Akif bin Aziz Rahimi. And then the last one is me, Muhammad Azamuddin bin Amran. First, I will talk about introduction. So, the introduction for the microporous ceramic membrane is a form of filtering technology utilized in many industrial processes, particularly in separation and purification applications. A type of ceramic membrane that has a pore size of less than 2 nanometer. Then, these membranes are valuable in filtration, ultrafiltration, and gas separation applications because of their ability to selectively separate particles or molecules based on their size due to their microporous nature. So these are the characteristics of microporous ceramics. So commercially available porosamic membranes show two main pore shape types. So the first is nearly straight pores and the second is tortuous pores. Now the applications of microporous ceramic membrane. First it was used in and used in oil water separation. Microporous ceramic membranes have shown to be effective in several instances when a comparatively little amount of oil or grease is present in water and has to be recovered. The second one is protein separation. Because of their better mechanical, chemical, and thermal resistance, microporous ceramic membranes are favored over organic membranes for some biotechnological applications such as protein separation and cell harvesting. Now the third one, for gas separation. The microporous ceramic membranes, due to their tiny pore size and inherent thermal stability, make them perfect options for high temperature component separation from gaseous mixtures. Operating gas separation at the feed gas as it increased inflation is frequently more cost effective than using organic membranes, which need a cool down or heat up cycle. So now I will pass to the next presenter, Prasan Kumar.
Thank you, Azam. So, I'll be talking about the evaluation of materials. So, our evaluation of materials topic is going to discuss about the suitability of materials for carrying out the separation method to form the microporous ceramic membranes. So, this evaluation highlights on the drawbacks and limitations of the materials for carrying out the separation method. Next. So here we have listed few limitations and drawbacks. So the first one will be fouling. Fouling is a problem with microporous ceramic membranes because proteins and other contaminants can build on membrane surface, resulting in a decline in separation effectiveness over time. Fouling can be produced by protein absorption on membrane pores, decreasing their long-term efficiency. And then the second one is brittleness. Ceramics are fragile materials by nature. Because of their brittleness, microporous ceramic membranes are more prone to damage during handling, installation, or cleaning procedures. Brittleness may necessitate cautious handling and maintenance to avoid fracture. And the last one will be and the third one will be cost. High quality microporous ceramic membrane manufacture can be costly. The expense of producing and processing ceramic materials may be a disadvantage, particularly when compared to alternative membranes materials. Cost considerations play an important role in the viability of large scale applications. And then the next one will be narrow pore size distribution. It might be difficult to get an accurate and narrow pore size distribution in microporous ceramic membranes. Pore size variation can have an impact on the selectivity and efficiency of protein separation processes. And then the next one will be limited flexibility. In comparison to some polymeric membranes, ceramic membranes are hard and have limited flexibility. This lack of flexibility may be an issue in some situations where a more flexible membrane is required to accommodate changes in operating circumstances. And the last one will be limited chemical compatibility. Particular ceramics may be incompatible with particular chemicals or at severe pH levels. This chemical compatibility issue may limit the variety of uses for microporous ceramic membranes in protein separation, particularly when working with strong chemicals. So I'll pass the next slide to Akif.
Okay, thank you, Prasan. So my part is analysis, which first is these membranes, often made of minerals such as alumina, silica, zirconia, zeolite, and carbon, exhibit a range of unique features that make them very appropriate for various separation procedures. The second one is the objective of this analysis is to provide a true understanding of the potential uses and inherent limitations of microporous ceramic membranes by delving into their material properties and forming process. Next is the material properties. Microporous ceramic membranes are commonly produced from materials including alumina, silica, zirconia, zeolite, and carbon. They are suitable for separation application because of these qualities. So, as we can see at the slide, the five material which is alumina, silica, zirconia, zeolite, and carbon are low at density, thermal conductivity, dielectric constants, uh, and they are high at thermal stability, strength, permeability, chemical resistance, and wear resistant. So I give to my friend Ain. Thank you.
So thank you, Akif. I will present about the forming process. So extrusion, pressing, slick casting, salt gel, and chemical vapor deposition are the typical techniques used to prepare ceramic films. And ceramic membranes functionalized with nanoparticles have been produced for oil and water separation. So precipitation technique for making an asymmetric skin type reverse osmosis membrane and extrusion technique for creating a microporous polyethylene tube appear to be extremely different preparation methods. And phase inversion creates microporous membranes, which are necessary for protein separation, and lipid homogeneous polymer solutions comprising two or more components are transformed into a two-phase system through this process. The chemical vapor deposition, or known as CVD, was used to create composite membranes for gas separation that were composed of microporous tantalum dots, silica layers supported on mesoporous alumina substrates. Next, so the first forming process is extrusion method. So powder, plasticizers, binders, and other ceramic additives are made, stirred, and then subjected to a number of processes like vacuum purging and aging before being forced through a dye nozzle at a pressure of between 20 and 800 180 MPa to extrude the support into the desired shape. So as shown in this figure, the stages of making ceramic membrane support by extrusion method could usually be simplified into six components comprising mixing, vacuum puddling, aging, extruding, straightening, and drying, and the last one is the sintering. So for the pressing, because the slurry does not to be released into the system, the pressing approach is thought to be the most of straightforward for creating the ceramic membranes. And then this process involves employing a hydraulic pressing machine to press a dry powder mixture that has been combined with a pore forming aging unaxially. So a binder can be added to support the mechanical strength of the membrane. Ultimately, a heat treatment and sintering process are used to create a membrane free of cracks and deformation. So it has been investigated the use of the pressing technique to create tubular UF and MF ceramic membranes. So the next one is slip casting. The ceramic slurry was prepared using structural compounds such as calcinite, alumina, and tetragonal zirconia with an average diameter size of 0.5 and 0.3 nanometer respectively. So the commercial alumina used in the fabrication process consisted of 99.8% with small fractions of silica. Sucrose with a purity level of 0.08% was used as a porogenic agent. The next one is Soldier technique. So hydrolysis is the first step where the precursors and solvents are mixed together to form a solution. So and then the condensation in this step, the sole formation occurs. This is where the colloidal structures in sole are created, leading to the formation of a connected porous structure or gel. And then the gel undergoes one of three types of drying processes: supercritical drying, thermal drying, or freeze drying. So this type removes the solvent and forms either an aerogel, xerogel, or cryogel, respectively. The final step is calcination, and the dried gel is heated to high temperature to create the final microporous ceramic membrane product. And the last one of the forming process is chemical vapor deposition, which is CVD. So as you can see in this slide, it, at the fluid flow, this is where the precursors and diluents flow into the system. And then the precursors adhere to the surface of the substrate. And then energy is supplied to activate the process. And then the deactivated precursors spread across the surface. And the reaction occurs in the gas phase, leading to nucleation. And then reactions on the surface lead to the film growth. Byproducts are released from the surface and then the gases exit from the system after the reactions have occurred. So each step in this process is crucial for the formation of the microporous ceramic membrane. So I will pass to the next presenter, Akif. Thank you.
Okay, thank you, Ain. The last part is the conclusion. First is microporous ceramic membranes have demonstrated great potential in a variety of separation applications, including gas, protein, and oil or water separation. Second, this is due to their distinct material features and forming technique. Like any technology, they are not without restriction, though, such as the expense and difficulty of developing crystalline microporous materials into ultra-thin, flawless membranes. For the recommendation is first, strengthening the structural integrity of these membranes through innovative material compositions and better production technique in order to overcome problems like low mechanical strength and fouling susceptibility. Besides, by adding surface alteration to lessen fouling and strengthen the membrane's anti-adhesive qualities can greatly increase both their lifespan and performance. Continued work to optimize the ceramic membranes for size, distribution, and morphology may result in increased permeability and selectivity. And the last one is encouraging collaborative activities across academics, industries, and research organizations can expedite the process of surmounting these challenges. So that's all from us. Thank you.